In this presentation, I will be explaining about high impedance neutral or open circuit neutral. So I've got electric diagram in here. Here's 230 voltage I put as a standard voltage, and we have got a transformer that is connected to MCB RCD through red wire. I put a red wire. The red wire indicates as a live wire, which is connected to our load, which is 10 ohm, and the black wire goes back to MCB RCT, that is a neutral wire which I have denoted as a black color, and the black wire goes back to neutral bar and back to transformer, which has a resistance of 0.01 ohm from neutral bar to transformer. All the green lines indicate the earthing wire, and we have got MEN link from neutral bar to our earthing conductor. So we have got our earthing conductor of our transformer as well, which is on the left side of the screen, and we have got our conductor of our house at the right side of the screen. The resistance between two conductors of the transformer and our earthing conductor, I have indicated it as a 50 ohm resistance. So if I simplify this diagram, it will look like this. So we have got 230 voltage in this circuit with 10 ohm resistance, which is our load, and we have got 50 ohm, that is our earthing resistance, and 0.01 ohm, which is the resistance between neutral bar and the transformer. So if I simplify it using Ohm's law, we get the overall resistance of 50 and 0.01 as a 0.009 ohm. And if I calculate the current of the circuit by using Ohm's law, I'll calculate the current of the circuit, and I'll just fast forward the video, and I've got 22.979 ampere as the overall current in this circuit, which is flowing. And what I found is, with the Ohm's law, I found 229.7 volt across our load, and 0.3, just a 0.3 voltage potential difference between in our neutral bar and our earthing conductor. So now let us come to second situation. I've created a fault in our diagram. I've created a 20 ohm of resistance between neutral bar and transformer, which might be because of corrosion or loose wire. So it is a fault diagram with 20 ohm of resistance between neutral bar and transformer. So if I simplify this diagram to electric circuit, it would look like this. We have got 230 volt of standard supply with 10 ohm of resistance, that is of our load, with 20 ohm is between neutral bar and transformer, and 50 ohm is between the between the resistance between our two of the earthing conductor. So if I use the Ohm's law, and I can find like 14.285 is the um, equivalent resistance between 50 and 20 ohm. And if I use furthermore Ohm's law to identify the current, it will be 9.47 of ampere of current flowing through our circuit with 230 voltage. And if I want to find out voltage across our load and across our earthing conductor, that would be 94.7 voltage and 135.3 voltage respectively through our load as well as our earthing conductor. I did it by using Ohm's law. So if I want to find out current across our earthing conductor, that would be 2.706 ampere across the 50 ohm resistor. So if I come back to our previous diagram and look at over here, so we have got now 135.3 voltage and 2.706 ampere of current flowing through our earthing conductor. So every metallic surface of our appliances has potential to give this electric shock of 135 voltage and 2.706 ampere to whoever touches that metal surface. It is all due to the increase in resistance in our neutral neutral wire. That is what it is called, high impedance neutral. And now let us come to our third situation. In this situation, there is no connection between neutral bar and our transformer, so it's an open neutral circuit. So every current flows through the neutral bar, through the MEN link to the earthing conductor of our house, and from the earthing conductor of our house to the earthing conductor of our transformer, and back to the transformer. So if I simplify this diagram into an electric circuit, it would look like this. So we have got 230 voltage of our standard voltage, 10 voltage, 10 ohm is our resistance of our load, and 50 ohm is the resistance of our resistance between the two earthing conductor. So using Ohm's law, I would find out electric current through our circuit would be 3.83 ampere across the circuit, and further calculating I can find out voltage across the load as the 38.3 voltage, and voltage across our earthing conductor would be 191.7 voltage. So if I come back to our previous diagram, there would be 191.7 voltage flowing through earthing conductor as well as 3.83 ampere. So every metal surface of our appliances has the potential to give the electric shock equivalent of this this magnitude, 191.7 voltage and 3.83 voltage. So it has a very high risk of giving electric shock. So how do we eliminate this high impedance circuit? We can eliminate this by either by using high quality wires, or verification by professional personnel, or inspection through our professional personnel. So